Alright, let's go. Number 10. The Parity Betrayal. In 1956, Sung-Dao Lee and Chen-Ning Yang were not trying to overturn physics. They were trying to solve an annoying bookkeeping problem called the Tau-Theta puzzle, two particles that seemed identical in mass and lifetime but decayed into different final states, which shouldn't have been possible if a property called parity always held. Every physicist since the 1920s had simply assumed it did. The standard assumption was mirror symmetry, absolute and untested in the weak force. Flip any physical process into its mirror image, and the mirror version should happen exactly as often as the original. No exceptions. No one had bothered to check it in weak decay because no one imagined nature would care which hand it used. Lee and Yang proposed a test. Chen Sheng Wu at Columbia decided to run it herself. Wu cooled cobalt-60 nuclei to a fraction of a degree above absolute zero, aligned their spins with a magnetic field, and counted which direction the emitted electrons went. Wu, Ernest Ambler, Raymond Hayward, Dale Hopps, and Ralph Hudson published the result in Physical Review in 1957. The electrons came out preferentially opposite the direction of nuclear spin, favoring one side by roughly 20%. Mirror symmetry had just failed a direct experimental test. Skeptics reached for instrumental explanations first. Maybe residual polarization from imperfect cooling. Maybe geometric bias in the detector array. Wolfgang Pauli, told of the early rumors, dismissed the whole idea as nonsense before the data forced him to write a letter admitting parity was, in his words, dying. Every alternative explanation for the asymmetry was checked and eliminated within weeks. The effect was real, and it was large. Lee and Yang received the Nobel Prize in 1957, less than a year after their prediction. Wu, who ran the experiment that confirmed it, did not share it. Somewhere in your own body, right now, weak decays are happening inside your cells, and every one of them is quietly handed, favoring leftover right in a way no other force does. Why does nature discriminate by handedness in exactly one of its four fundamental interactions, and nowhere else? Wu's mirror had already cracked. Number 9 shattered it completely. Number 9. The Kaon Confession. In 1963, James Cronin and Val Fitch were not hunting for a broken symmetry. They were interested in a phenomenon called regeneration, how neutral kaons behave when they pass through matter, and had built a sensitive spark chamber spectrometer for that purpose at Brookhaven National Laboratory. Testing for stray CP violation was listed in their proposal almost as an afterthought, a secondary check while the real experiment ran. The standard prediction, reinforced by the parity work 6 years earlier, was that combined charge and parity symmetry CP still held even where parity alone had failed. The long-lived neutral kaon, K-long, was expected to decay only into 3 pions, never 2, because a 2-pion decay would require CP violation directly. Analysis dragged through the winter of 1963 into early 1964. When Cronin's graduate student Ren Turley finished combing through the data, the 2-pion decays were there, unmistakably there. James Christensen, Cronin, Fitch, and Turley published the result in Physical Review letters in 1964. Out of the long-lived kaon decays they recorded, roughly 1 in 500 went to 2 pions instead of 3, a small but statistically solid violation of CP symmetry. It was the first proof that matter and antimatter are not perfect mirror images of each other, anywhere, ever. The physics community's first move was suspicion, not acceptance. Maybe an unknown regenerating medium was contaminating the beam. Maybe the spectrometer had an undetected bias favoring certain trajectories. Lincoln Wolfenstein proposed an entirely new superweak force to explain it away, without touching the standard model's core symmetries. Decades of follow-up experiments closed every one of those doors. The violation was fundamental, not a leak in the apparatus. Cronin and Fitch shared the 1980 Nobel Prize for a result neither of them set out to find. If CP were perfectly conserved, equal amounts of matter and antimatter would have annihilated completely in the first fraction of a second after the Big Bang, and neither you nor anything you have ever touched would exist. What is it about the fabric of physical law that permits asymmetry at all? That question about broken mirrors gets one uncomfortable exception. Number 8. The symmetry that refuses to break. Number 8. The stubborn constant. Physicists at CERN's base collaboration were not trying to find new physics. They were trying to close a loophole, testing whether antiprotons obey the exact same rules as protons to see if some subtle asymmetry in matter and antimatter properties might explain why our universe is made of matter at all. Stefan Olmer's team built a penning trap system specifically to make that comparison as precise as physically possible, given everything already broken on this list. A reasonable person might expect antimatter's magnetic behavior to differ from matter's by some tiny telling amount. CPT symmetry, the combination of charge conjugation, parity, and time reversal together, is supposed to be an untouchable law, one that survives even after its individual pieces fail separately. The base team measured the magnetic moments of the proton and antiproton against each other. They matched, not approximately, to a precision of about 1.5 parts per billion. Olmer and the base collaboration published the comparison in Nature in 2017. Proton and antiproton magnetic moments agreed to 1.5 times 10 to the negative 9. Finding zero evidence of the CPT violation, many theorists quietly hoped might appear. Separate tests using neutral kaon mass differences pushed CPT precision even further, into territory measured in parts per 10 to the 18th power. Here, unusually, there is no failure parade, because nothing failed to explain. Nothing needed explaining. Every attempt to detect even a hint of CPT violation across multiple independent experimental methods and particle systems has come back empty. Some theorists propose that string theory or quantum gravity should introduce tiny CPT-violating terms at extreme energies. None have been found, not even close. This is the item on the list that should unsettle you differently, not a crack in the foundation, but a foundation tested this hard and still holding. Every version of a mirror universe casually imagined in fiction, antimatter people, reverse causality, depends on CPT staying intact. It has, so far, without exception. If CPT is truly absolute, what does it mean that everything else on this list keeps finding a way to be defiant? One unbroken law standing next to 9 broken ones is its own kind of clue. Number 7 breaks something nobody thought could bend at all. Number 7. The detector built for the wrong discovery. The Super Kamiokande detector in Japan was constructed primarily to catch protons in the act of decaying, a prediction of grand unified theories that would have been one of the biggest discoveries in physics history. Atmospheric neutrinos, the byproduct of cosmic rays hitting the upper atmosphere, were treated as background noise, something to model and subtract, not the main event. The standard model, as written through the 1990s, predicted neutrinos have exactly 0 mass, and treated the 3 neutrino types as fixed, unchanging identities from creation to detection. A muon neutrino created above the detector, and a muon neutrino created on the opposite side of the planet should arrive in equal numbers. They didn't. Neutrinos coming up through the entire diameter of the Earth were arriving at roughly half the rate of ones falling straight down. Takaaki Kajita presented the finding for the Super Kamiokande collaboration at the Neutrino 98 conference in Takayama, and Yoji Fukuda and collaborators published the full result in Physical Review Letters in 1998, a zenith angle dependent deficit consistent with muon neutrinos changing identity, oscillating into a different flavor, mid-flight. That transformation is only possible if neutrinos have mass, something the Standard Model's authors had built the theory to explicitly forbid. Early skeptics proposed detector geometry effects, uneven efficiency at different arrival angles, or contamination from unrelated particle showers. Years of cross-checking with the Sudbury Neutrino Observatory in Canada, run by Arthur MacDonald's team, confirmed the same oscillation pattern using an entirely different detection method with solar neutrinos instead of atmospheric ones. The deficit was not instrumental. Neutrinos genuinely change what they are while traveling. Kajita and MacDonald shared the 2015 Nobel Prize for a discovery the original experiment wasn't even designed to make. Roughly 100 trillion neutrinos are passing through your body every second as you hear this, a portion of them mid-transformation between identities that the Standard Model insisted could never change. If a particle's fundamental type isn't fixed, what other properties we call fixed are just averages we haven't watched closely enough? If identity itself can drift mid-flight, symmetry can vanish just as quietly. Number 6 goes looking for it and finds nothing, which turns out to be its own kind of unsettling. Number 6. The silence that cost millions. The Acme collaboration, based at Harvard and Yale, set out to measure something almost absurdly specific: whether the electron has an electric dipole moment, a tiny asymmetric distortion in its charge distribution. Many supersymmetric extensions of the Standard Model predicted this distortion should exist at a detectable level, offering a possible sideways route to new particles the Large Hadron Collider might never directly produce. Standard quantum electrodynamics predicts the electron's dipole moment should be vanishingly small, far below what any current instrument could ever measure. But many beyond Standard Model theories predicted it would be just large enough to catch. If new heavy particles were quietly influencing the electron at short range, using cooled thorium monoxide molecules to amplify the sensitivity of the measurement, the Acme team searched, and found nothing. The Acme collaboration published their result in Nature in 2018, an upper limit on the electron's electric dipole moment of 1 times 10 to the negative 29 electron centimeters, the most precise null result of its kind ever recorded. That number alone eliminated entire families of proposed particles that theorists had spent decades building models around. Proponents of low-energy supersymmetry initially argued the effect might simply be smaller than their models assumed, adjustable with a tweak to particle mass ranges. Successive refinements to the experiment closed off those adjustments one by one, ruling out broad swaths of parameter space that had once seemed the most promising place to find new physics. Nothing rescued the predictions. The silence held. A null result sounds like nothing happened, but an absence this precise is a verdict. Dozens of proposed particles, invented to solve other problems on this very list, were quietly executed by a molecule sitting in a vacuum chamber. What does it mean that our best guesses at what lies beyond the Standard Model keep failing the same way, not through contradiction, but through simply not being found? Absence proved to be a weapon. Number 5 is the opposite problem, a number sitting in plain sight that physics cannot explain at all. Number 5. The impossible cancellation. In 2012, teams at Atlas and CMS at the Large Hadron Collider were completing the last piece of the Standard Model, hunting for a particle predicted back in 1964 by Peter Higgs and others to explain why particles have mass in the first place. The goal was confirmation, not confusion. Find the particle, close the chapter. The Standard Model itself gives no clean prediction for the Higgs boson's exact mass, but the quantum corrections that pile onto it from every other particle in the theory should, left unchecked, drag its mass up near the Planck scale, roughly 10 to the 19th GeV. The energy where gravity itself becomes as strong as the other forces. They found the Higgs. Its mass sat at approximately 125 GeV, 17 orders of magnitude lighter than raw quantum corrections say it has any right to be. To keep the Higgs mass that light, unrelated quantum contributions from wildly different physics have to cancel each other with a precision better than 1 part in 10 to the 34th power. Every term would need to align to roughly 34 decimal places for no evident reason. Physicists call this the hierarchy problem, and it is considered one of the largest fine-tuning coincidences ever documented in physics. Supersymmetry was proposed specifically to cancel those corrections automatically, pairing every known particle with a heavier partner that would neutralize the runaway math. Decades of LHC searches have found no supersymmetric partners at any accessible energy. Extra-dimensional theories offered another cancellation mechanism. None of their predicted signatures have shown up either. The number sits there, uncancelled by any known mechanism, just correct. Every atom in your body has mass because of the Higgs field, tuned to a value physics cannot derive from first principles and can only measure. You exist inside a 34 decimal coincidence nobody can explain. Is it a coincidence at all, or evidence of a mechanism we simply haven't found yet? A number this fine-tuned demands an origin story. Number 4 is the biggest fine-tuning problem of all, the very fact that anything exists to measure it. Number 4. The universe that shouldn't have survived its own birth. Cosmologists modeling the earliest moments after the Big Bang were originally trying to calculate something mundane, the abundance of light elements like hydrogen, helium, and lithium, and how that abundance matched observations of ancient stars and the cosmic microwave background. It was meant to be a consistency check on Big Bang theory, not a crisis. Standard particle physics predicts the early universe produced matter and antimatter in essentially equal amounts. Equal amounts should have collided and annihilated each other almost completely, leaving behind a universe of pure radiation and nothing solid at all. That isn't what happened. A universe of matter exists. Stars, planets, and everything are hearing the sentence. Measurements from the Planck satellite's map of the cosmic microwave background pin the imbalance at a baryon to photon ratio of roughly 6.1 times 10 to the negative 10, about one extra matter particle surviving for every billion matter-antimatter pairs that annihilated. That tiny sliver of surplus is the entire physical universe. The Standard Model does contain a mechanism for generating exactly this kind of asymmetry through the same CP violation Cronin and Fitch found in Kaons back in 1964. The problem is scale, calculated from known Standard Model physics, that CP violation is too small by roughly 10 orders of magnitude to account for the surplus actually observed. Proposed fixes involving heavy neutrino decay or extra CP violating phases in unseen sectors remain unconfirmed by any direct experiment. Every proton in your body is a leftover from a near total annihilation event that consumed nearly everything else that ever existed. You are, quite literally, statistical noise that never got canceled out. What tipped that balance, and why did it leave behind exactly enough matter for a universe capable of eventually wondering about it? That leftover matter needed a rule to survive at all. Number 3 is the exact rulebook cosmologists wrote to explain how, and the rulebook still doesn't add up. Number 3, the missing ledger. In 1967, Soviet physicist Andrei Sakharov was not trying to write a checklist for cosmology as we now use it. He was working through the theoretical requirements any universe would need to end up matter-dominated at all, largely as an exercise in consistency rather than an attempt to solve the observed asymmetry directly, since the imbalance itself wasn't yet firmly measured. Sakharov derived 3 conditions that any successful mechanism must satisfy: baryon number violation, sufficient C and CP violation, and a departure from thermal equilibrium in the early universe. Satisfy all 3, and a matter-dominated universe becomes possible. The Standard Model does technically contain all 3 ingredients. None of them are strong enough. Not one. Sakharov published the conditions in a short 1967 paper in the Soviet journal ZETF Pisma, later translated and reprinted in JEP letters. Decades of subsequent calculation confirm that Standard Model CP violation, the same effect Cronin and Fitch measured, falls short of the asymmetry actually observed in the universe by roughly 10 orders of magnitude. And the Standard Model's phase transition is too smooth to satisfy Sakharov's 3rd condition at all. Proposed patches include leptogenesis, where heavy right-handed neutrinos decay asymmetrically in the early universe, and electroweak baryogenesis assisted by new Higgs sector physics. Neither has direct experimental confirmation. Every accelerator search for the extra CP violating physics these models require has come back with tighter limits and no discovery. Sakharov wrote down the rules that explain your own existence, and 60 years of physics still cannot find enough of the ingredients his own rules demand. The recipe for a matter universe is known. The missing quantities are not. What is quietly supplying the rest of the asymmetry? Somewhere physics hasn't looked yet. That missing ledger might be hiding inside a single number, currently under the most intense scrutiny in particle physics. Number 2 watched that number move, and then watched it get taken away. Number 2, the anomaly that almost was. In the late 1990s, physicists at Brookhaven's E821 experiment were doing something almost routine by particle physics standards. measuring the muon's magnetic moment as an extremely precise test of quantum electrodynamics, expecting the result to simply confirm decades of prior calculation. It was meant to be a check, not a discovery. The Standard Model makes an extraordinarily precise prediction for how a muon's magnetic moment should wobble in a magnetic field, built from contributions of every particle in the theory acting through quantum loops. Any deviation from that prediction would mean particles the Standard Model doesn't know about are contributing too. E821 found a deviation. Small, but real. A 2.6 sigma disagreement, tantalizing but far short of proof. The experiment moved from Brookhaven to Fermilab in 2013 and returned a first result in 2021 that pushed the combined discrepancy to 4.2 sigma. Runs 2 and 3, released in 2023, pushed the combined significance past 5 sigma, the traditional threshold for a discovery, against the older Standard Model prediction. For a moment, it looked like the clearest evidence yet of something new hiding in the quantum loops. Then the theoretical side moved. The Muon G2 Theory Initiative, using updated lattice QCD calculations, published a revised Standard Model prediction in 2025 that differed from their own earlier value by roughly 3 standard deviations. Fermilab's final measurement, released in June 2025 with a precision of 127 parts per billion, agreed closely with that revised prediction. The anomaly that had defined a decade of anticipation didn't get disproven exactly. It got quietly absorbed by better math. 10 years of expectation collapsed not because an experiment failed, but because theorists corrected their own arithmetic. Somewhere between 2 competing calculations, a discovery of new physics evaporated. How many other confirmed anomalies in physics are just waiting on someone to finish a harder calculation? 9 broken symmetries, 1 impossible number, and 1 discovery that vanished under its own theory. Number 1 asks what happens the day one of these doesn't vanish. Number 1. The signal nobody is ready for. Every experiment on this list was run by physicists who were, in some sense, hoping to be boring. Confirm the Standard Model, close the chapter, move to the next measurement. Almost none of them expected to find what they found. That is precisely why each result carries weight. Accidental discoveries resist the accusation of bias in a way that deliberate hunts for new physics cannot. The Standard Model, taken as a whole, predicts a universe with no room left for surprises at these energies. Every deviation on this list, the muon's wobble, the Higgs's impossible mass, the missing antimatter, the electron's stubborn silence, sits inside a theory considered essentially complete since the 1970s. And yet the deviations keep clustering in the same direction. Small, persistent, and just outside the threshold of certainty. Across dozens of independent experiments spanning 6 decades, from Wu's cobalt in 1957 to Fermilab's muon in 2025, the pattern is consistent. Each anomaly gets measured more precisely. Some resolve into agreement, like CPT. Some resolve into disappointment, like the Muon G2 revision. None has yet resolved into an unambiguous 5 sigma and holding discovery of a genuinely new particle or force. Optimists argue we are one better detector away from confirmation. Skeptics argue every one of these anomalies is destined to dissolve the way the muon result did, killed by a more careful calculation rather than a new particle. Both camps have been right before, about different items on this exact list. If even one of these becomes real and confirmed instead of quietly absorbed, it rewrites particle physics for the first time in 50 years, and it happens in your lifetime, discovered by someone doing something as mundane as calibrating a detector. The universe has been leaving these threads dangling for decades. What happens the day someone finally pulls the right one? Every entry on this list came from someone who was trying to do something else entirely. Wu was testing a colleague's hunch. Cronin and Fitch were chasing regeneration. Kajita's detector was built to watch protons, not neutrinos. None of them went looking for a crack in the Standard Model. The cracks were waiting for them anyway. The universe is not confused about its own rules. We are the ones still assembling the ledger, one accidental discovery at a time, and the ledger still doesn't balance. If you want to see more videos like this, click the video on screen now.